So yesterday the lecture was a bit heavy. Bethe Ansatz. I don't know whether you repeated the calculation for your own sake. Today I'll try to do something lighter, and then we'll use the Bethe Ansatz to calculate something. I want to tell you again, because Sanjib already taught you that, he told me, about large deviations. In fact, one of the aims of this series of lectures will be to compute large deviations. So I want to tell you again about these objects, these mathematical functions, which are becoming more and more important in statistical mechanics, especially for systems out of equilibrium. So let's start, but again I think you already saw that, but it's good to see it again. Let's start with the simplest case. If you have n independent, identically distributed random variables, IID, independent, identically distributed random variables, and let's take a very simple example. We take them to be binary variables. Epsilon I can be +1 or -1 with probability P or Q equal to 1 minus P. A priori nothing to do with the exclusion process, just independent random variables, and we want to compute their sum. So we are going back to the first course of the first year of statistical physics, the very, very beginning. So I want to compute the sum of them. This is a random variable which takes value between -n and +n. And we can say quite a few things about that. But one main result is that if you average Sn, this will converge towards the average value of epsilon, any of the epsilons. This is simply the law of large numbers. If you toss a coin, head and tails, a perfect coin which can fall on both sides with equal probability, 1/2, 1/2, you toss it 1 million times, you will roughly see 500,000 heads, 500,000 tails. But not exactly. There will be some fluctuations. Can you tell me what will be the order of fluctuations if I toss a coin 1 million times? So 1,000. Okay? So there will be root n fluctuations. So this is a law of large numbers. Classical law of probability. I think it's Laplace in the 19th century. But you can refine it. You can say, okay, I will subtract the average value. But now I have to scale by square root of n. That you can easily, in fact, compute even the variance of Sn, because it's just the sum of the variances of all the epsilons. The variance of epsilon is 4pq. So in fact, if I even rescale it, this is just a number, it's not so important. But 4pq square root of n, this will converge towards a Gaussian with 0 mean. And because if I rescale things correctly, the Gaussian will be normalized. So with unit variance. So normalized Gaussian variable. Okay. And in fact, this is the only thing we really use and need when we do basic statistical mechanics. We don't go beyond that. And this is almost, this is really kind of, you don't need to learn mathematics to do that. I think everybody knows that. Even if you're not a mathematician, this is common wisdom. This is slightly more elaborate, the central limit theorem. But this is again common sense if you wish. But I may ask you a more refined question. Suppose I toss a coin, a perfect coin, head and tails, 1/2, 1/2 probability, 1 million times. What is the probability that I get 1 lakh head and 9 lakh tails? This is possible. This is not impossible. Okay? So what is the probability that Sn over n, so the relative fraction of head or tails or this value, takes something, a value r, which is between -1 and n, and 1, but which is not a typical value p minus q, half head, half tails, okay? Anything, something untypical. Well, you can do the exercise here. It's infinitely simple. It's just a binomial distribution, Stirling approximation, and you will find that this thing for large n behaves like exponential minus n times the function phi of r, and this function phi of r is positive because this is a probability, so it's a number which is less than 1. If r is equal to, so phi is positive. If r is equal to p minus q, which is a typical value when n becomes big, what is the value of phi? What can you say about phi? If r is equal to p minus q, what is the value of phi? Well, the theorem of the law of large numbers tells you that this probability will go to 1. Okay? So phi has to vanish. Typically of order 1 over n, but at pi minus q, we are always at large n. This function has to vanish. And typically phi will have a potential type of shape. Phi as a function of r will vanish at the typical value. It will be positive, and in fact here it will even be convex. So it's a convex function which vanishes at the stationary value, at the typical value. So it's a kind of potential, if you wish. I mean, something you roll in the bottom of when you reach the typical value. That's exactly what a potential does for us. Something which confines things and is optimized, is minimized for the typical value. Okay, you can do the calculation here, and I can just give you the result. It's very simple. Phi of r using Stirling. I mean, this is an exercise, less than an exercise. It's something absolutely all of you should be able to do. Again, r is the same r. Over 2q. This is the formula, and you can check it's convex, it's positive, it vanishes at p minus q, and so on and so on. So phi has a name. Again, mathematicians do not use the same name as physicists. It's called a large deviation function. So you see, it's a kind of very general object which somehow puts the law of large numbers and the law of the central limit theorem into a more quantitative basis. It tells you how fast this behavior is reached. Okay? And in fact, if you make an expansion of phi near the minimum, so it will vanish, its derivative is 0 because it's always positive. If you assume that it's a well-behaved function, smooth, you make a second order expansion of phi near the typical value or critical, then you will see that it can be written n r minus a constant r minus r critical square, and this is nothing but the central limit theorem. So this large deviation theorem, because it's not always true, I just gave you an example very precise, but when it is true, and mathematicians have proved it under weaker and weaker assumptions, so it's a very general scheme. When this is true, this is something which goes much beyond, much farther than the two usual basic theorems that we learn when we are kids. So this is a kind of refined object, this large deviation function. Here I just defined it in a purely mathematical manner. But the nice and the funny thing is that this started to play a very important role in physics quite recently. So I will not multiply the examples, especially that Sanjib already told you about that, but I don't know. I mean, I can give you some exercises or things to compute by yourself if you wish. For example, if you just take a random walker on an infinite line, asymmetric, which jumps with rate p and rate q towards the right and the left. So of course you have the side n here. So you have the master equation, d dt of Pn is p, Pn minus 1, q, Pn plus 1, minus p plus q, Pn. And suppose you start at time t equal to 0, you start at site number 0 at the center, and you call x of t the position of the walker at time t. The walker at t. So the speed, the average speed during time t will be given just by distance divided by time, and of course the average speed will converge to p minus q. P equal to q, there is no average speed, almost surely. So this is really like the central limit theorem. But you can ask yourself, okay, I make experiments, I measure x of t, I divide by t, so I get an empirical value of xt over t. It can take any value between minus 1 and plus 1. So what is the probability that the speed comes out to be v? V being any number between minus 1 and plus 1. Could be any number, of course. The typical speed will be p minus q, but something unusual can happen during one experiment or a few experiments, and you could get a non-typical value of v. So here you see it's the time which is a large variable. So when time goes to infinity, again this will behave like exponential t. Okay, let's call it g of v. G of v again is a large deviation function, and I just ask you to compute it if you wish. I mean, so you did that more or less. It's continuous time, discrete time. So continuous time is slightly more complicated, but it can be done. So the formula is a bit awful, but it's not. Again, it's a kind of basic exercise. So it's given by q plus v over 2 log q over p minus, I mean, if you do this exercise, I think you will, yeah, you will see how it works. Minus v square plus 4pq square root minus, so even for such a simple problem, you see that the expression is not so simple. So it's not at all something which is Gaussian. And it tells you about non-typical behaviors of the speed. Okay, v square. Okay, so try to compute that if you have some spare time. So it's a positive function again. It vanishes for the typical value p minus q. It is convex, and it has a nice property which is maybe not totally obvious if you look at it like that. It is not an even function of v. If you change v into v minus v, it's not the same thing, but there is a nice relation between g of v and g of minus v. The difference is not 0, but it's linear. It's v log q over p. You can check it. Does anybody knows why this is true? Have you ever heard about this? Here I'm just telling you, here is a crazy function. It has this very simple symmetry. Does anybody of you know why? It's not a trivial reason, far from it. But does it ring a bell to anybody? No? Does it remind you something, this kind of, huh? It is a fluctuation theorem. It's a Galavoti-Cohen. So this is just an example of the Galavotti-Cohen Evans-Morris, Galavotti-Cohen Evans-Morris fluctuation theorem. So this is just a simple special case, but this is a so-called fluctuation theorem, which I think I'm not going to teach unless we can discuss about it. Maybe the last day I can talk about it, but I mean this is a general, very general relation which is true for many, many large deviation functions. These large deviation functions are not even or odd functions, but almost. I mean, if you take the difference, then what remains is just linear, multiplied by some coefficient, which depends on the problem that you study. And this is a very, very important theorem. It looks very innocent like that, but it's very general, and it contains Einstein fluctuation dissipation relation. It contains Onsager reciprocity relations, and much more. So this is maybe the major, with Jarzynski identity, which is a bit related to it. This is a major result in non-equilibrium statistical mechanics, general result for the last 20 years, by far. But okay, I'm not proving it here, but I'm just telling that, of course, you can see it on this very simple example. So if this relation is true, of course, going back to the definition, you can rewrite it in another way. Remember that G of V was defined as the probability of observing an empirical speed equal to V. So if you just use now this relation, this tells you that the probability of observing a speed V divided by the probability of observing the speed minus V is just exponential T V log of P over Q, if I didn't make any mistake in my signs. And this is maybe a more familiar form for the fluctuation theorem, taking the ratio of the probability of seeing something divided by the probability of seeing the opposite, minus V. This probably is much more familiar to a larger number of you. But this is perfectly equivalent, you see. You just to use the definition, use that, get that. Did you tell them about that already? No? Okay. So of course, I mean, 6 hours of lectures could be devoted, 6 lectures, 9 hours could be devoted to all this field. I'm going to do that. But this is a huge field. Okay, now let's continue to look at some examples of large deviations and try to, for the moment being, this was purely mathematical or probabilist. Of course, this is physics, the fluctuation theorem. This lecture room, okay, and it's a volume V. It's at temperature T. It's surrounded by a uniform thermal reservoir at temperature T, and there are n molecules of air in this big room. So of course there is an average density, n over V equal to rho 0. And I know the typical value of this average density, 1 mole for 22 liters at normal temperature. But suppose I do an experiment and I take a much smaller volume, small v, typically 1 liter, somewhere in the room, and I count how many particles I have in this smaller volume. Okay? So I just do an experiment, and I do it many times, again and again. So as usual in statistical mechanics, small v is very small with respect to the whole volume of the room, 1 liter compared to meter cubes, okay? But it's large enough so that it contains many, many, many molecules of air, okay? So if it's of order of 1 liter, it contains 10 to the power 22 molecules of air. So as we write usually, V is much bigger than 1, one being just the interparticle distance and much smaller than the total volume. So I measure the number of particles. It will be a fluctuating number. Of course, on average, I will get rho zero small v, of course. But suppose I want to measure the empirical density. I make an experiment, I count the number of particles, I divide by v, and I want to measure the empirical density. Something odd could happen, it's very unlikely. I could get an empirical density which has a significant difference with rho zero. It's 80% of rho zero. Suddenly particles, I don't know, go away from my experimental vessel. So what is the probability that my empirical density, rho, has some value which is not necessarily the typical, the characteristic value rho zero. So as you know, you understand the scheme, this thing will be exponentially small in v, small v, multiplied by a function. So what kind of name? I call it again phi. Phi of rho. And of course, it's a large deviation function. It will vanish when rho is equal to rho zero. So it's again a function which is positive, which vanishes for the typical value, but it measures non-typical fluctuations of density in my small experimental device. Okay, now a question, do you know what phi is equal to? Can you guess what it is? I will show it to you in 1 minute. But you see, this is very nice, because somehow free energy has appeared out of the blue without talking about thermodynamics, Carnot cycles, whatever you wish, entropy, the basic thermodynamics, without having to talk about ensembles. When you learn about physics, statistical physics, you have all this ensemble machinery to learn, and canonical ensemble, microcanonical, grand canonical, blah, blah, blah. It's coming purely from just a probabilistic, or if you want, even empirical kind of question. And more generally, even entropy that we learn about in physics can be reconstructed by asking a correct probabilistic question, more akin to this Poisson distribution, in fact. This would give you more the entropy. And Gibbs free energy, Helmholtz free energy can be reconstructed like that by fixing not the temperature but the pressure or things like that. Okay? So the very nice point is that thermodynamic potentials can be realized, can be built as large deviation functions. So in fact, how do you compute that? How would you do that? I want to leave that as an exercise. So take it, we'll discuss about it in the afternoon session if you wish, but I think it's a good exercise if you can try to think how you would compute that as a pure problem in statistical mechanics. So of course, I ask you to do the things now upside down. You know statistical mechanics, you know about partition functions, you have learned all that. So what is the probability that in a big volume V, I find in a smaller volume small v, I find n particles, using the usual apparatus of statistical mechanics. Okay? Try to do that. There's only one thing that you need to know, that you have to assume that you have only short-range interactions and not long-range interactions. So you will compute the probability of seeing n particles here and large n minus small n here. So you will have to compute how many configurations of your gas, whether it is perfect or not, it's not really important. How many configurations will be such that small n are here, large n minus small n are here, and sum over the energies, do statistical mechanics, and then you should get the following result. I give you the result, if I can find it. You have to do some expansions and so on, but you will find that this phi, so please do it. So this you didn't teach them? No. So because if you already know, then tell me. So this would be the free energy per unit volume minus free energy evaluated at the typical minus compressibility. So it's a free energy up to a linear thing. What is F? F is, I think there's a KT probably. So I put a KT. So beta F is minus beta F is the free energy per unit volume. No, not beta, this is non-dimensional. So F, sorry, is the free energy per unit volume. So you're using extensivity here. That's why you need to have only short-range interactions to be able to use extensivity. So if you have a free energy F of V, T, N, you can write it V, small f, rho, and T. Okay? So try to do this exercise. Now we can ask a more general question, which is in fact very similar to what Satya taught you this morning. It's amazingly similar. So I think it's just seeing the same things said in different words. Instead of putting one volume of 1 liter in my big room, I will just tile my room with plenty of small boxes. So now I will have my room here filled with air. It's really the coarse graining procedure that Satya just told us about an hour ago. And I will put plenty of small volumes, one after the other. V, first box, and I put M boxes, which are the same M, V over small v boxes. Okay? And I can ask a similar question. What is the probability that I have N1 particles in the first box, N2 particles in the second box, N3 particles in the third box, and V and NV? So the probability of having N1 particles in first box, in box 1, N2 particles in box 2, and NM particles in the last box. So I put boxes of 1 liters everywhere, and I want to calculate this probability. Of course, I don't really want to calculate this probability. I prefer to talk about densities. So what is the probability that I see density rho 1 in the first box, rho 2 in the second box? So it's better to talk about the probability of seeing density rho 1 in the first box. It's the same question. Rho 2 in the second box, rho m in the mth box, in the last box. So you see it's a kind of more refined question. Here it was a 1 box, now I have boxes everywhere. Of course the total number of particles is conserved, it's a closed system. And here again I ask you to do the exercise. In fact this is simpler. Bizarrely, this is simpler than the other one. The algebra is simpler. And this you can prove that again it has a large deviation form. So it will be exponential minus small v, the volume of each box, which is big enough but very small with respect to the whole. Well, I can put a large v, in fact. It's a question of, yeah, let's put large v. This will be a m and n. And it will be now a function not of only one variable, but all these n variables. Rho 1, rho 2, rho n. Okay? Is it clear? Are you following? Yes? So now this function can be computed, again using basic statistical mechanics. We try to do it, and otherwise we shall talk about it. It's quite simple. And you will find, if you do the exercise, that this function is given by, so it has to be dimensionless, beta is 1 over kt, of course, divided by m, the number of boxes. That's why I changed small v into big V. sum of I equal to 1 to m, free energy per unit volume, the same object as here, computed at rho I, temperature T. It's a canonical ensemble. Huh? So the average value, I call it rho 0 here, but because there's rho I, it's always confusing, let's call it rho bar, the average density. Otherwise you'll tell me what is I equal to 0, or I don't know what, so let's call it rho bar. So it's just you evaluate the free energy for this non-typical density rho 1, rho 2, rho m, but you subtract the typical free energy. So just the deviation from the typical free energy. Okay? Again, this is very, very basic physics. But it's nice because now we can ask the natural question, which is, it's just multiple. Yeah, if you want, exponential of a sum is a product of exponential. Yeah, you're right. It's, yeah. Again, because we assume short range interactions. So each box is separate from the others. You're right. So now we can, of course, let m going to infinity. We consider that v is very, very small with respect to a large v, and we pave our room by very, very small boxes, and the room is very, very big. Okay? So we take, so now it will become a profile. The question that we are asking here is what is the probability of observing a continuous profile in my room, which changes from point to point. So just taking the limit rho of x, which changes from point to point. So I take very small volumes of 1 centimeter cube in a very, very big room. So again, this is very, very similar to what Satya has done this morning. It's almost the same thing. So it's a coarse graining. And you will, just by taking the limit of this function, so it's a total volume multiplied by a functional of the profile. And what is the functional of the profile going to be? Can you tell me? So now it's a large deviation functional. I gave you examples. It was a function of 1 variables, then it became a function of m variables. Now it's a function of a continuous profile, so it's a functional. These are just words. So can you tell me what it is? What is the limit of this thing? So it will just become beta 1 over kt integral, okay, of f dx, f of small f of rho x t minus f of rho bar t. Okay? Just the continuous limit of the previous thing. And as you can really see, this is, I'm insisting, but this is very, very similar to what we learned this morning. It's very, very similar. So here you see this is now, this is really, really the free energy. I mean, before we had some spurious terms and so on, because we took only one box. The two boxes were very different. I mean, in fact, here in this, it's kind of stupid question, but there are 3 boxes here. The big box, the small one, and the complementary. That's why we have these kind of extra terms. But if we take now boxes which pave the whole room, we have something which is very nice and which is really the free energy, the local per volume, per unit volume. Okay? So, well, so now the logic is, it's not logical. The assumption is, I think I have convinced you that potentials of thermodynamics and equilibrium statistical mechanics can be built using this large deviation concept. Okay? And there are even some books which really take this point of view. They forget about ensembles, they forget about Carnot cycles, which I find very sad because I love Carnot cycles, but okay, not only because he was French, I think it's just beautiful. But okay, they take the point of view of large deviations to build a lecture or a full course in statistical physics. But the idea is that these large deviation functions, they don't care about equilibrium, non-equilibrium. They can be defined for many processes. And I think Satya will tell you about large deviations in the random matrix theory for the largest eigenvalue. And so you can define this question of having non-typical behavior for many things. I mean, equilibrium has nothing to do with it. It's a mathematical problem. But what people believe now is that although basic concepts of thermodynamics such as entropy, free energy have no meaning for systems out of equilibrium, can you tell me, for example, why entropy cannot be defined for the pipe model? Suppose I have two reservoirs at different temperature with a current flowing. Just can you give me a physical argument why entropy has no meaning here? Two temperature or two potentials, two different voltage, 200 volt and 0 volt. Why is there no entropy? Can you give me a physical, good, can I say, common sense reason why there is no entropy? Yeah, but even a more common sense than that, more basic. Because you could say, okay, I will define entropy here, 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 here. But in fact, no, it's meaningless to talk about entropy. Why? There is no? Yeah, but this is not common sense. I'm asking you a very common sense thing. Well, a common sense argument, of course you can buy it or not, but suppose you have a current, electrical current which is going, okay? So if there is an electrical current which is going here because of, who did that? Fourier, I think, I don't know. Well, you know that there is heat generated. I think it's Fourier effect. RI squared is power, RI squared T is the heat. If I is the current, R is the resistance, or ohm, I don't know who did that. This is the power which is dissipated as heat in time T. So there is always heat which is generated. Okay, I'm going to be very floppy, but entropy is delta Q over T. But there is always heat which is generated. There is no entropy. Entropy is just continuously growing, if you wish. So you cannot talk about entropy in a system when there is some electrical current. At best, you could talk about entropy production per unit time, maybe. But no absolute entropy, because you have always heat which is generated and put into the reservoir at temperature T, if you want, the atmosphere. So entropy is always growing. So there's no good value of entropy in this problem. Maybe again many people talk about entropy production, rate of entropy production per unit time, but no entropy. So if there is no entropy, there is no free energy, there is not much, okay? So you cannot talk about these things, but you may talk about large deviations. So coming back to this pipe model, precisely, that have flown, having flown from left to right, from A to B, during time T. Okay? So what can you say, again, naively, physically, if I divide this total number per time? This will give me the typical current, the average current, like before we had the average speed. So this will be the typical current, okay, in the large time limit. This will converge to the typical current. And what do you know about this typical current? Huh? Ohm's law, for example. Ohm's or Poiseuille or Fick or whatever you Fourier, you know that this is typically proportional to the difference between V1 minus V2 divided by the length of the system multiplied by some constant. If V1 and V2 are not too different from each other and will remain at the linear order. So we know things about this typical current, but we don't really know how it fluctuates and we don't know its probability distribution. But we can ask the same type of large deviation questions, we can say, okay, I do an experiment, I measure the current that it has given to me, and what is the probability that I observe something which may not be at all the typical current. Something. Ohm's law tells me that I should get, I don't know, 1 ampere, and what is the probability that I get 2 or 1/2? So again, this thing will take a form of a large deviation function. Still write it like phi. Of course, it's not the same phi. Phi will be positive. It will vanish for the typical value. For the most probable, which for in the long time limit will really be peaked as being the typical most probable and so on. But I have some information about deviations. And the idea is that this phi here, for example, so here is a system out of equilibrium where I cannot talk about entropy, about free energy, anything like that, but I can define very simply a large deviation function for the current, and the hope is that this phi somehow carries information which is very similar or of the same type to the information carried by thermodynamic potentials in equilibrium statistical mechanics. So here is a good candidate for being a non-equilibrium potential. And as I showed you, in the case where these things are equal, so we have a vanishing current, we have an equilibrium system, then phi can be identified to one of these equilibrium potentials. Free energy, Gibbs energy, entropy, whatever you like. So it's something which is the object we know at equilibrium, which can be defined out of equilibrium, and somehow we want to learn about it. So we want to compute it, for example, or want to have knowledge about it. Okay, what else can we do? Maybe this I will do slightly later. Another question we can ask is not about the current, but about the profile. So suppose again that I have my pipe model, and I have two potentials, temperatures, whatever I wish. Suppose they are not equal, and these are two temperatures. What will be the temperature profile typically from left to right? It will be linear profile. Okay. So if the temperature is higher here, it will be something like that. Just by Fourier and phenomenology, Fourier law, dt, the second derivative of the temperature is 0. Okay, diffusion law, whatever you like. In the steady state, okay, in the long-term limits. But we can very well ask the question, I don't know, don't take it too seriously, but I don't know why I prefer when it goes like that. Just reverse the signs, it's not important. It's easier to draw. Now we can very well ask, what is the probability of seeing a profile like that? Why not? Instead of seeing the typical linear profile, what is the probability of seeing a profile rho of x? This could happen. Okay? This is exactly out of equilibrium the question that we just asked about boxes just 10 minutes ago. 10 minutes ago, we know that on average the density is going to be completely flat. We have rho 0, rho bar everywhere. But we may ask about the fluctuations of the profile, a different coarse-grained density profile. So now we can ask the same question for a system out of equilibrium. Out of equilibrium, we know that there is a linear profile. But we can ask, okay, what is the probability that it has this stupid shape? So what is the probability in this non-equilibrium context? But as you can see, it's exactly the same question that we asked at equilibrium 10 minutes ago. What is the probability of seeing rho of x? So again, it will scale like exponential minus the size of the system times some functional, which is not the same, of course, but I write it the same way. Some functional of this profile. Okay, do you buy it? Is it clear? Yes? If we were at equilibrium, V1 equal to V2 or T1 equal to T2, this would be exactly the same problem that we did before, and we know that F would be exactly the free energy of the system. The integral of small f rho x t dx minus the average value. Just I showed you. So here I think we can reasonably say that we are really trying to compute something which is a perfect analogy to the free energy, but for something which is out of equilibrium, for a problem which is a non-equilibrium system. Okay? So this is a kind of sound definition of free energy for a non-equilibrium model without having to talk about entropy, without having to talk about Carnot cycles or whatever. Heat, work. It's a purely probabilistic problem, but at equilibrium it gives you back free energy. Out of equilibrium it gives you something which exists and which should be a kind of generalization of the free energy for non-equilibrium systems. So okay, all this is words, but of course one should do something concrete. One should try to compute these things for a non-equilibrium system. So this was done, for example, for the, of course you will say, but this is the only case I know where it was done. I mean, the only non-interacting n-body case, interacting, where we have a symmetric exclusion process. This is an equilibrium in the bulk, but we have two densities, rho 1, rho 2, which are different at the boundaries. So 2 days ago, or yesterday, I talked about these rates alpha, beta, gamma, delta. But alpha, beta, gamma, delta, they can be related to left boundary density and right boundary density. I will not give you the formula, but there is a precise formula. But if I remember, I don't remember, I think if you put alpha and gamma here, something like rho 1 is something like alpha over alpha plus gamma, and rho 2 is beta over beta plus delta. I don't remember. Just do it by yourself. You will find it. Just, yeah, something like that. And so you can, instead of talking about these rates, you can just put densities. And you can ask yourself, what is the probability of seeing any profile? So again, the typical profile is a linear profile. But you can ask yourself, okay, what is the probability of seeing something arbitrary? And this is, again, exactly the calculation, not the same because the context is not the same, but exactly the same procedure that Satya told us this morning. What you would have to do is to forget about this lattice, which is very small. So you take the limit of a very large system. You coarse grain your system. So you take small boxes of length dx or dl, which contain many lattice sites. And you want that the density here, near site I, which is x over L, L being the system, x is equal to I over L. You want that the density is given by rho of x. Okay? But the difference with the calculation of the entropy that we learned about this morning is that here, first of all, we don't have a uniform measure. I mean, this morning, Satya told us that we have to put these n points by putting n1 into the first box, n2 in the second box. So we have a multinomial coefficient. We use Stirling approximation, and we got a sum of rho log rho. Okay? So here you have to be careful because it's not uniform, the measure. In fact, the measure for this exclusion process is given by the matrix ansatz. So given a profile, you will have to compute the sum over all configurations which are compatible. Is that the word you used? Compatible? You use another word, I don't remember, but it was a synonym, which are consistent, not compatible, consistent. So you will have to compute the sum over all configurations which are consistent with this density profile. Okay? The only difficulty, which is a major difficulty, is that unfortunately each configuration does not appear with the same probability. It's not uniform probability, but it's a probability measure which is given here by the matrix ansatz, because we had a stationary state. In the case of Satya, this probability was given by the Wigner measure, Wigner-Dyson measure. So very similar problem. Once we know the basic, the atomic distribution, we don't care at all if it's Gibbs or not Gibbs or matrix or Bethe or Wigner or Dyson. The intellectual procedure is the same. Of course, it's technically very difficult. And I can assure you that here it's horribly difficult. But it has been done. It has been done by famous people, Derrida, Leibowitz, and Speer in 2002. So the paper is very technical, so I'm not sure, I mean, I recommend you to read it. You have maybe some more basic things to learn, but they found a formula for this functional, for this non-equilibrium, so-called free energy, if you wish. It's not completely rigorous to call it free energy, but free energy analog functional. And they found something which is quite complicated. So let's just write the formula. Maybe you don't maybe even have to copy it. Plus just look at the structure. So okay, B is a function which is known, a function of two variables. As usual, you will always find this P log P coming in this game because Stirling is hidden everywhere anyway. So you will always find a similar structure, whatever you have, almost. So you still have a structure which is very similar, but not quite. So this is a function of two variables. Rho of x is the profile, but I have to tell you what f of x is. Okay? And f of x is a very complicated function. F of x is obtained by solving a differential equation, a nonlinear ODE, which really looks awful. It's yeah, it's awful. I just write it, but again, it's not. But it's just to tell you that it's highly, highly non-trivial. So you see, and you have some boundary conditions. F of 0 is rho 1, f of 1. We have rescaled the size of the system to 1, is rho 2. So you see, even if the procedure is the same as before, the result is completely different and is quite complicated, but it's quite explicit. You know everything if you want. I mean, numerically, you can get f as a function of your profile, your candidate profile. So f is a function of the profile. Then you substitute everything into that, and this gives you the functional, the large deviation functional of the profile. Now you can do some expansion. So it's a non-equilibrium. So it's quite complicated because you can show, for example, that it's non-local. Before, the formula in the equilibrium case was local. F of rho of x t minus dx. Here, because of this differential equation, f at some given point depends on rho everywhere. So it's completely non-local. And even there are certain cases where it's not convex. It's quite complicated. But you can do, I mean, don't do it, but these people for us did it. If you have a almost at equilibrium system, so close to equilibrium, or even rho 2 equal to rho 1, then you can really solve everything here. In fact, you will find that f is a constant and so on. And if rho 2 is equal to rho 1 is equal to the average density, you will find back your equilibrium free energy, which in this case is really given by what Raoul said. because in case of equilibrium, you can really put the particles, the measure is uniform, you can put them anywhere. And in the case of equilibrium, you just get your usual 1 minus rho log 1 minus rho plus rho log rho. Okay. So you get back the equilibrium case. So these are the kind of objects we are interested in. And as you see, for the probability, the large deviation of a profile in the stationary state, we don't need to do any time-dependent problem. We just need to know the stationary measure, however complicated it is. It can be an extremely technical problem to convert the knowledge about the microscopic configuration probabilities for each configuration to a coarse-grained macroscopic distribution. It can be horribly difficult, but we don't need to know any time-dependent thing. Now if we are interested in the current that has flown from left to right during time t, we need to know about time-dependent evolution, because we are counting how many particles since the beginning of times of the experimental time up to time large t, how many particles have flown from left to right, and this is a non-equilibrium time-dependent question. And there we shall need the Bethe Ansatz. Here we don't need Bethe Ansatz. Okay? We need only stationary probabilities. So this is what I want to do. Number of particles that have flown from left to right during time t, I want to know that. I want to know this object. Did I call it G or phi or phi? I want to compute this large deviation function. Okay, there's something else I can compute which is closely related to it. And again, I'm trying to overemphasize it, but one idea also is that you are undergoing a series of lectures that may look very different, but many of the underlying techniques and language and so on are the same. So yesterday, by the end of his lecture, Shumik Das told you about these perturbative expansions, and he told you about some cumulant generating function, and somebody asked him about one particle irreducible diagrams and so on. I'm not going to talk about diagrams, but I'm going to use the same language, not of diagrams, but of cumulant generating function. You see, this is something which characterizes the probability distribution of yt over t. Another way is to know the probability of yt. Well, this is almost the same. Up to rescaling, this is the same thing. But another way to characterize the probability distribution is to know the average, the variance, the third moment, the fourth moment, and so on and so on. So another way that you learned about, which is equivalent, I just check the notation. No, not gamma, because gamma is something else. Mu. You can take the generating function of the moments of y. If I make a formal expansion with respect to mu, I will generate all the moments, and so on. Okay? So if you know that, morally, by Laplace transform inverse, you know the probability distribution, because this is just the integral of the probability of y exponential mu y dy. So this is the moment generating function. Something which is quite useful is a log of this. And this is the cumulant generating function, and this is the thing that Shumit was considering yesterday afternoon. So again, if I just do a formal expansion, it starts the same, but the second order, because you have squares and so on, this is simple. The second order would be the variance, and the higher orders will be the higher cumulants. Not the moments, but something which are combinations, non-linear combinations of them, squares here, which we can write like that, the cumulants. But again, the same information is encoded in this object. Okay? So I can compute this. And what happens often, and I will show that later, in the problem that we are considering, so this is a general formula, but here what happens often is that in the long time limit, it takes a much simpler form. There is a kind of Lyapunov exponent, maybe this name is familiar to you. This thing behaves like exponential t some e of mu. I'm going to prove it for the exclusion process, but it happens quite often like that. So it means that if I take the log, this is just equal to t e of mu. Okay? But now if I expand e of mu in terms of mu, it's just t. Okay, for mu equal to 0 is the average of 1. The average of 1 is 1, so e of 0 is 0. So it starts as its first term. So e1 mu, e2 mu square over 2. I just expand my function. And then you can see, okay, e1 is nothing but the average. e1t is the average of y. The variance of y is t times e2. So more generally, the nth cumulant grows linearly with time. If I have this property, then I know that the nth cumulant will grow linearly with time. So if I divide by time, and it will be given by the nth term in the Taylor expansion of E. Okay? The important thing mostly is the second one, the variance. But okay, you can ask the question for all of them. Now the thing which remains to be done, and it's quite easy to do, is if I know the information of E, how do I get any knowledge about phi? Okay? Well, they are related by Legendre transform. The good old Legendre transform of stat-mech and thermodynamics. Did you do that? Yes? So maybe I will not do it again. By saddle point. Okay, so I don't do it. So they are related by Legendre transform. And the idea is that instead of computing the large deviation function at the beginning, we shall calculate this object. And then we shall deduce the large deviation function by Legendre transform. Okay, so let's start doing that. So this was, yeah. So now it will become slightly more technical, but we'll probably not finish the calculation at all. A closed system. For technical reasons. Because, as you remember, I taught you about we need time-dependent properties. So we need to diagonalize the Markov matrix. Bethe Ansatz can be used for the closed system. For the open system, it can, but it's just awful. It's beyond, okay, it's very, it's horrible. So let's do it for the closed system. Okay. So we have to define the current. There are many ways of doing that. So we have n particles over L sites, as usual. L sites, n particles. And now we have to define the current. So one very natural way would be I sit here and I count how many particles traveled positively and minus those who traveled negatively. But here we shall talk, and it's quite equivalent. But if you sit here and look here, you will somehow introduce a non-homogeneity in your system, which is a source of technical difficulties. It can be done. So I will call YT the total current. And what is the total current? It is the total displacement of all the particles between time t and 0 and t. So what does it mean? Is that, so again, counted with signs on P and Q. This is the positive direction. If a particle jumps forward, I will increment YT by +1. If a particle somewhere jumps backward, I will subtract 1 to YT. So YT plus DT is equal to yt plus 1 if a particle, there's only between t and t plus dt, only one particle can jump, because two jumps are dt square, not possible. If a particle jumps forward, jumps in the positive direction, minus 1 if a particle jumps backward with priority q, and if nothing happens, it remains the same. Up to an overall factor L, it is the same thing as looking at the current through one bound, but it's a homogeneous problem. Okay? If you look precisely at what this means, this means that your Markov operator, in fact, you have split it into three terms, three blocks. Your Markov matrix, it contains diagonal terms which make nothing, because you remain in the same configuration. It contains hops in the positive direction, somewhere a particle goes forward, and it contains hops in the negative direction. A more complicated problem, you can always think about it, would correspond to a different splitting of the Markov operator. Okay? But this is a basic splitting. So what we can do now is to define the probability to be at time t in a given configuration. This is the basic object, but with yt taking the value y. So what is the probability that at time t the system lies in configuration C and yt takes the value y? This is very, very redundant. I can just write y here. The probability of being in configuration C, because at time t equal to 0, y0 is 0. Nothing has happened. I'm starting. And that my random variable yt, my counting variable, takes the value y. Well, you can write a Markov equation for that. This is still a Markov, this is a joint Markov process for in a big space, configuration space and total current space. Now, because I can have backward and forward jumps, y can take any value. It's an integer, but it can take any value, in fact, between minus infinity and plus infinity. You can even think that even in a finite time, something very odd can happen and many particles can jump forward. So it's unbounded. You can take any value. It's very unlikely that it takes a huge value, but it's possible. And you can write a Markov equation for that. Writing the Markov equation is not more difficult than writing the usual one, but you have just to be very careful about what kind of jump you have done between time t and t plus dt. Whether your jump has been a forward jump, a backward jump, or a diagonal term. So I just write the result. Try to convince yourself. Again, I think I don't want to explain that because this is elementary. I can explain it to you if you ask me individually or during exercise class. I just first write it, and I think then you will find it simple to understand. So these are the forward jumps. These are the backward jumps. And these are the null jumps. The jumps which do not affect. So in fact, C prime is equal to C here. But okay, let's write it in very general terms. So I have split my Markov operator into three parts. These are the jumps where from going from C prime to C, one particle has gone forward. So y has been incremented by 1. These are the jumps where one particle has gone backward. And here are the jumps where no particle has moved. So in fact, no particle has moved. It means that in fact these are only the diagonal terms. Okay, so C prime is equal to C. But suppose I ask a different problem, and instead of counting all jumps, I count only the jumps through a given bound, then this will contain all jumps that do not occur through the bound that I'm looking at. So it's slightly different, okay? But it's the same idea. Okay, so you have to solve this Markov equation. But it's not, now it's in the operator M, because y can take infinite number of values, it's an infinite system. So it looks horrible. But fortunately, the rates here do not depend on y. Okay, it's a simple problem. So do you have any idea of how to do that? There is a technique. You have rates which are independent of y. You have y plus 1, y minus 1. Well, the idea is to Fourier transform or Laplace transform with respect to y. Because you have translation with respect to y, and if you Fourier or Laplace transform, you will just get some factors. So the idea, which is quite natural if you think about it, is to define an intermediate quantity, which is nothing but, okay, like Satya before, I prefer Laplace and Fourier because you don't have to carry these i's and so on and so on. So it's easier to consider a quantity that I will call p hat t, c, and mu, which is just the Laplace transform with respect to y of these things. Okay. By exponential mu y and sum over y, I will observe that this pt hat of c and mu satisfies a very simple equation where mu is now just a spectator. It will satisfy an equation like that: m of mu times ptc hat and mu, with m of mu is m0 plus exponential m plus exponential minus m minus. Just do it. This is very simple. And now you are back to a matrix which is finite, which is typically 2 to the power n, 2 to the power l, by 2 to the power l, or ln squared. Because it is just the for mu equal to 0, you have the original Markov matrix, and you have slightly deformed it. What have you done exactly? You have taken your Markov matrix, the diagonal has not been changed. All the p's which are off diagonal have been multiplied by exponential mu, and all the q's have been multiplied by exponential minus mu. So here there is a nice physical interpretation. Mu is a fugacity of the jumps, and each positive jump is counted with its exponential mu, and each negative jump is counted with its exponential minus mu. So mu is really a fugacity of the jumps. It's a dual variable. In fact, you're going to a kind of grand canonical ensemble with respect to the jumps. So here I have been very systematic, I hope, and very specific to one model. But you have to remember one thing that some of you may encounter during your research. What have we done? We started with the dynamics. We were interested in some observable, y, current, something else if you wish, some correlation. Here it's the current. And in the end, to compute the statistics of this observable y, we have introduced a joint probability distribution. But by doing some manipulation, we've ended up in a system which looks very much alike the original system, but where the dynamics has been deformed. So we have deformed the Markov matrix. So this is a deformation of the original operator, Markov operator. So we have deformed the original Markov matrix. And this deformation, of course, depends on what you're looking at, on the observer y. If I look at something else, the deformation will appear differently. For example, if I could have double jumps, I would have a matrix m plus and m plus plus, and I would have exponential mu, exponential 2 mu. Okay? If I want to count the absolute value of jumps, positive, negative, I don't care, how many jumps? Can you tell me what would happen if I just count how many jumps and I don't subtract positive and negative ones? Just the activity. People call this the dynamical activity. Some people are very keen on this dynamical activity or frenzy of the system. So I don't count the current, but just how many elementary events occurred in the system. Can somebody tell me what would be the deformation? Without doing the calculation, just they developed a general large deviation theory in a very general context with any observable, with some, of course, mathematical hypothesis, and this idea that you deform your operator according to the observable you're interested in is something extremely fruitful and extremely general. So this is what we have done here. Sorry? Ah, okay. Okay. Yeah, mu is a potential, chemical potential. So let's now come back to our elementary problem of the exclusion process. You gave me some minutes more, yeah? Is in the matrix. What's happening? Are you hungry? You shouldn't be. You think I'm hungry? Okay. So the Markov, no, so this is not a Markov matrix anymore, because columns do not sum to 0 unless mu is equal to 0 or 2i pi. Okay, so it's not a Markov operator, but it's still an operator with positive values of diagonal and diagonals which are negative. So it still satisfies the Perron-Frobenius theorem, which tells you that it has a unique dominant eigenvalue. I mean, if you look at this problem, it's still of the usual form. Twiddle. Okay, so I can still solve it by taking the exponential of this matrix. So the solution is still given by Pt is exponential m of mu t, p t equal to 0, twiddle. And because the Perron-Frobenius theorem tells us that there is a unique dominant eigenvalue, so there is a maximal eigenvector and a maximal eigenvalue that I will call E of mu. Not by chance, it's the same as before, as you will see immediately. And there is a maximal eigenvector, so m of mu, f mu is an eigenvector with eigenvalue E of mu. Okay? And in the long time limit, again, it's a finite matrix, there is no degeneracy, Perron-Frobenius tells us, P twiddle t will behave like exponential E mu t times f of mu. Okay? Only the dominant eigenvector will remain. And more precisely, if I just write precisely what it is, okay? But remember, what was P twiddle? P twiddle C of mu was the sum of exponential mu y, P t C and y. Okay? So P twiddle C and mu was just a sum over y, exponential mu y, p t, c, and y. This is only in the large time limit, of course. Now suppose I sum this over c. So I take all the components of this vector and I sum them. Then I will have a double sum. Summing over C just eliminates the variable C. I have the marginal of the distribution of y. So this is just the sum over y of exponential mu y probability of observing y. But this is nothing but this thing, which is the object I'm interested in from the very beginning. Okay? So it means that the sum of the components of this vector B twiddle just give me this thing, which is the main object I want to compute from the very beginning, which is the Legendre transform of the large deviation function, which is a characteristic function of y. But now if I do the sum, again Perron-Frobenius, but it's not a big deal. I mean, Sanjib has worked on that. There can be some horrible things happening, but here nothing horrible is happening. Perron-Frobenius tells us that the components of the vector f are positive. They remain finite with of normalization. So what I know is that the sum of these entries will be dominated by this exponential factor. And the sum of this is finite. Odd things can happen, but okay, not here. One has to be careful always. So we know now that this thing, and I have proved that to you, this behaves like exponential E mu t. Okay? And as I told you half an hour ago, E mu is the cumulant generating function up to factor t. So if I know the function E of mu, I know the cumulants of my variable, and if I Legendre transform E of mu, I have the large deviation function. Okay? And now, what have we gained in all this blah blah? Well, we have gained the fact that we started from a purely probabilistic problem. Large deviation, cumulant generating function. And thanks to all this deformation of operator, writing and so on, we have converted our purely probabilistic question into an eigenvalue problem. I mean, I have just told you that this E of mu, which is the cumulant generating function, is nothing but an eigenvalue of a known matrix. And in physics, we love eigenvalues. We spend our time computing or diagonalizing matrices. Okay? And we have plenty of techniques and methods for getting eigenvalues. So we have converted a purely probabilistic problem, this one, or the associated large deviation problem, into a problem of computing the eigenvalue, the maximal eigenvalue of a given operator. And by chance, again there are many techniques, but in this case, by chance, this operator M of mu, which is a good deformation of the Markov operator, happens to be integrable. This operator M of mu can be diagonalized by Bethe Ansatz. So here is our good old diagonalized by Bethe Ansatz. So now here is where Bethe Ansatz enters the game. We shall use the Bethe Ansatz to extract the dominant eigenvalue of M of mu, and by extracting it and studying it, we'll be able to get information about current fluctuation and current cumulants in the exclusion process. Okay? So here now starts applying the Bethe Ansatz problem. Fuse them, use the Bethe Ansatz, extract E of mu, and get some physical results. So I'm not going to repeat the Bethe Ansatz procedure for this matrix. The thing is that yesterday I taught you the coordinate Bethe Ansatz, which is quite heavy, and that's life. But to solve this problem, we shall use a much more sophisticated but much nicer looking version of the Bethe Ansatz, which is called the functional Bethe Ansatz. Yesterday we got some equation for the z's. Zi to the power L is the product of Pzi minus Qzi Zj plus blah 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 divided by blah blah blah. But there's a way of rewriting that as a nice functional equation, okay, which is just one line, and where no z appear, It's just a functional equation. So this is the thing I'll probably teach the next lesson, and then show you how to extract statistical information about the current and about the system and about large deviations, thanks to the Bethe Ansatz. I think I will stop here. Yeah. Any questions?